divergence of a vector field, being a dot product, will always come out to be a scalar, or you can think, the word scalar bugs you, scalar function. It can come out to be a function, like a function of x, y, and z. A scalar function, not a vector field. So, let's try it. Well, I'm going to use something similar that we saw, or simple that we saw earlier today. That when you find the divergence of that vector. Remember, these are vectors. But, if you take the dot product of a vector with a vector, you get a scalar function. I'll let you try it. I do want to point out, you will find doing divergence a lot easier than doing curl. Aren't dot products easier?
Uh-huh.
Dot products are way easier. Del. Dot. Okay, well, here's del. What's del?
2x.
D. 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 And if you don't mind, I'm going to put F right underneath. Because you know when we do a dot product, it's this times this plus this times this plus this times this. Do you recall that curl of this vector field was 0? Well, the divergence isn't 0. What's the partial of that with respect to x? Here it comes. So this is divergence of vector field. I get 2x plus 2y plus 2z. That's it. I hope you find divergence real easy to compute. Compared to the curl takes a little more.
What does that measure?
That's a great question. So that's why I wanted to make sure to put this down on a document. Everyone, I'm going to read this to you. This is from the textbook. You know, what does this represent? The divergence of a vector field represents the net rate of change with respect to time of the mass of a fluid flowing from the point x, y, z per unit volume. So in other words, the divergence of the vector field actually measures the tendency of the fluid to diverge from the point x, y, and z. The tendency of the fluid to diverge from x, y, z. And in terms of our course and the application here, Andrew, Gauss, who was a brilliant mathematician, Gauss came up with just an awesome theorem called Gauss's divergence theorem. The last thing we'll do in this course, where we use this to help us evaluate surface signals. So that's a really, real huge application. But right now, it's like that's what it does in terms of measuring something. Okay. So we're not good with that? That's the divergence of the vector field. It's funny because divergence always goes fast. Try this one.
But don't you need to dot it?
Oh, go ahead.
Don't you need to multiply them for dot products?
You're right. So I did the derivative of that, this times this, but I was thinking, what's the partial of that with respect to x, which is just 2x.
Okay.
And then I just wrote it. So you're right, I did this times this plus this times this plus this times this, but then I evaluated it.
No, but again, you have it with the vector. Don't you have to dot it with the vector, like divergence?
Oh, you're right. I'm going to put a dot right there. But when I dotted it, it was like when we do a dot product,
Oh,
del dot that, I'm like, it's this times this plus this times this plus
Okay,
this
now I
times this.
see it.
But you are correct, it's like, I got to do that, multiply to that. But I'm thinking, oh, that would be the partial of that respect to x, give me that.
Gotcha.
The reason I wrote them underneath each other, because I thought it was easier for you to go, what's that partial with respect to x? What's that partial with respect to y? I could have put this over there, right? Which you absolutely, I could have done this. But you still would have had to do what? This times this, plus this times this, plus this times this. Oops. Hey, so try this one. Now, I hope this goes fast. Actually, give that one a shot. Wipe this out. What's the divergence of this vector? Because it's funny, even in that section, when it's going to be 16.9, Gauss's divergence theorem, we'll get to. You'll get vector fields like that.
3,
And you'll find that doing the divergence is not too challenging.
3,
30. Partial with respect to x is a what?
1.
Partial with respect to y is a? The partial with respect to z is a? So you notice doing a divergence of a vector field real easy. I mean, even this. What if these were all Q's? I mean, I could have put other letters in there, but these are the kind of things you're going to see. You'll see them in there. You go, wait, how do I do this again? You might have to go back to your notes just to refer this, because this is section 16.5. What do you get for this?
3x squared
3x squared plus.
y squared plus this squared.
And you'll take this, when we get into section 16.9, we'll do something with that. It's going to help us evaluate some surface areas. Awesome.
So you said that divergence represents the tendency for a particle to move in a specific direction.
Exactly, and I want to give you a copy of this. Just so, I want to write down, like, it's really the wording from the textbook, so you can actually articulate very well and understand exactly what it means. You see that? It's way at the bottom.
You're right. So like this last one, we got 3 as the final answer, and the one before was an actual function. So
Yes.
Is it just like plug it, like if you had a function like at this point?
Yes, you said at this point. Good job, man. It would be some x, y, z coordinate. Where in the one where we just got a 3, it would be the same at any point.
Right.
Outstanding. That's where it gets affected by at the point. Matt, very good. Hey, we're now going to do an exercise and determine whether or not we have a vector. We can just put a v. A scalar. We can just put an s. Or if it's just totally meaningless. So can we make up a key? First of all, what does this mean? What's del of f? Del of f is a,
Gradient.
yep, gradient of a function is a vector.
Okay.
So let's just make sure we understand that. Everyone agree? Del of f is vector. All right, what's gradient of function? Isn't that the same thing?
Mhm.
Gradient of function, or grad of f, is vector. This is what you're going to see, and I just didn't want it to bug you. So del f is vector, and notice I do a lowercase f, del f function. These mean the same thing. I got them right there, they're vectors. And when you see a cross product, or a dot product, what it has to be on either side, no matter what. A vector has to be on this side, and a vector has to be on this side. A vector has to be on this side, a vector has to be on this side. And what is vector cross vector?
Vector.
You get a vector. What is vector dot vector? You get a what?
Scalar.
Scalar. But anything else, we're just going to say meaningless, okay? So this is page 16.5. I'm going to take the actual problems from the book. They go quick. I won't rush you. There's some tricky ones in here. I want you to be careful. Here's the first one. So I'll do all these. They've got A, B, C, D. I think I got enough room. Again, for your answer, you can just write V, S, or how about for meaningless? We'll just put an M. That sound good? Check out letter A. Take it slow. I just know in the past I've done these on tests. If you didn't go back to review this, they sometimes miss. They're just guessing. I didn't want you to guess. So I'll make sure to give you enough practice here for this. What's a curl of, is that a vector?
Mhm.
Is that a scalar? Or is that meaningless?
Vector. That's a vector.
Someone's going to catch it.
Meaningless,
How do you know?
because F isn't a vector.
Hang on. Oh, got it. So we're going to add something to it. I know it's tricky, so don't worry. What has to be up to the word curl? Curl of vector field equals vector. So you're like, you can't do curl of a what? Function. So hey, let's add it to our list here. Like this is our key. Let's add it down. And curl, what must be after this word?
Vector.
No matter what, there has to be at least some vector field notation. Same thing with DIV. What has to be after this DIV? Has to be a vector. Whereas curl of vector field is vector. Divergence of vector field, but what has to be after that curl? So we're being like, what's our answer letter A?
Meaningless.
This is totally meaningless, but that was tricky, right? I know, because we say F and F, F and F, and that's lowercase f. But curl of a function, nothing. Has no meaning. Super job. Hey, B. Okay, I bet you all get this. GRAD, lowercase f. Gradient of function. That's a vector, do you all agree?
Mhm.
That's a vector. Yeah. We recognize that gradient of function is a vector field. You can even actually find it. You can find that vector field, right? I'm making up some examples. All right, let's see. They go quick, but slow me down if one bugs you. Wait, how'd that happen? Divergent of a?
Scalar.
You're good. And you all are flying. All right. And it was tricky. There's probably going to be a few more. I think they did. No, I don't think this one's tricky. I bet you get this. Curl, parentheses, grad, lowercase f. Gradient of function.
It's a vector.
That's a vector. What's curl
Of a vector.
of a vector?
Vector.
Vector. Meaningless vector, scalar vector. And you're flying. Good job. Everyone okay with that? Curl of vector is a vector. That's a vector. This one concerns me. That's the one I worry about. So you staring at Brad, way to go. I wouldn't stare at that carefully. Because I keep saying grad f, don't I? I keep saying grad f, gradient f. I keep saying it all over and over, gradient of f. I'm talking about lowercase f, like a function of f. Like that right there. Even me, when I'm writing this on the board, I want to make sure that's that lowercase f for some function of x, a scalar function. Gradient of a scalar function is a vector. GRAD, can you ever have that afterwards? No, it's not like curl and divergence. This is totally what? Meaningless. What has to be right there?
Lowercase.
That has to be a lowercase f. By the way, it can't be del of a vector. It's got to be del of a function, right? And there's del. It's the partial with respect to x, y, and z of some function. Hey, that was good. Any others? Yeah, let's do a few others. GRAD, DIV, F. GRAD, DIV, F. Hey, on a test, I make the vector fields full-face print. So I think that's easier.
Meaningless. That's a meaningless.
Let me start. We're going to take it slow. Do the parentheses first. What's divergence of the vector fields?
Vector.
Divergence of a vector field is a
Scalar, sorry.
scalar function.
Sorry.
Now, I say scalar, but you might want to put the word function with it. Think like some scalar function. Like scalar function. You know, like what did we get earlier? X plus y plus z. What we got an x. We had a 3x squared plus 3y squared plus 3z squared. So some kind of scalar function. Well, that's like an f. You all agree? So we're finding the gradient of a.
F, yeah.
This exists, and what is it?
Vector.
This is a vector. Someone catch that? We say scalar, but we got oh yeah, like a function, like a scalar function. It can be a constant, but sometimes you get f equal to x plus y plus z or something like that. And this comes out to be a vector. F had meaning it's a vector. You were a vector, you were a vector, you were a vector. Meaningless, scalar, meaningless. Hey, you got it. Hey, we can just do a couple more of these. G, DIV, GRADF. And it's lowercase f. Let's see, what's gradient of function?
That's vector.
That's a vector. A vector field like f, right?
Uh-huh.
Does everyone agree? Gradient of function is a vector. What's divergence of a vector field?
Scalar.
Scalar? This is a scalar. This has meaning. Does that make sense? Excellent. All right, one more. I'm taking letter H. No, we should do more. GRAD, DIVF. Another I. Curl. Curl. of F. What do y'all think? I hope you get this.
Meaningless.
You're the best. Someone see this?
Uh-huh.
That's totally bogus. You can't do that. Divergence of function out. So this right here, totally meaningless because of that. How about this one? Curl of a vector field.
That's a vector.
Vector. What's curl of a vector?
Vector.
Vector. You wanna table all those? Hey, on the practice sheet, you'll notice, I think I did a bunch of those. I figured, I knew, this is one other area I'm like, I noticed in previous courses, it seems like, can you give me extra practice for that? So number 14, I did an A, B, C, D, E, F, G, H, I, J, K, L, went down to M, just to keep going and going. And you can check them, just something you can check if you want to do that, it was up to practice as well. So great job with this. So the only thing left we gotta do is, can we look at a vector field and get an idea of what's going on with the curls or the divergences? So I'm gonna pop up that screen, if you don't mind, just so we can look. And I can write them on the board. These are not hard vector fields to draw, so when I'll put this up, if that screen's bugging you, I'll put it up on the board. That'll work. Let me shrink it a little bit. This is actually number 9 for the textbook. Look at the light. And I'll erase this, and eventually I can just copy. This is not a hard vector field to draw on the board. We can convert it to the board, but I want you to see it on the screen first. Get all this out of the way. We need our definitions. Curl and F. They actually define both. So this is what they're asking you to do. We'll start with number 9. And this will not be a hard vector field for me to duplicate up on that board. But I want you to see it first. Someone see these? Are they blue? Okay. These blue vectors. It looks like this is some vector field. They said the vector field F is shown, but they said it's in the XY plane, as we can tell. But they did say it looks the same in all other horizontal planes. So how about the plane right above?